Hi, Assalamualaikum. My name is Muhammad Zafir Azibi Azman. My matric number is CF190176. We are from Group 1. We'd like to present about our group project for subject Structural Steel Design PFC 44903. For the group works, we are divided by each member. Uh, for the AutoCAD, Azizi Yusri are conducted to do the design. And for the Step Pro, uh, I do the design process, and other member are doing some part of some for the calculation and the some of the reports. From the group discussion that we do, we are agreed that design concept that we choose, we're using dual pitch spread truss. This is a simply out layout in AutoCAD for our volleyball stadium. As you can see, this is a plan view of the volleyball stadium. This is the front view of volleyball stadium. All the dimension, all the materials, all the design, we are discussing during the minute meeting, and we are agreed that this is our design for volleyball stadium. This is the structure layout for the front view of the level volleyball stadium. As you can see, this dual pitch practice, and this is the roof plan of the plan view. For this is a 3D view of the volleyball stadium that we're using by Step Pro. As is, you can see this design that we create by Step Pro, design of the volleyball stadium. For the load that we use in calculation that we put on the truss and all the member. As you can see at the top chord of the truss, the dead load that we use is 1.6 kilonewton meter square. The variable load is 0.76 kilonewton meter per square, and the wind load is 2.29 kilonewton meter per square. For the bottom chord, the dead load that we use is 3.05 kilonewton meter. The load combination at the truss, as you can see here, is ULS max 1, ULS max 2, ULS max 3, ULS min, SLS 1, SLS 2, and SLS 3. All the load computation that we are put in this calculation, all that we are discussed during the minute meeting, and we are agree with the load. This is a calculation for the member. The member that we choose here is member 120 and 121. As you can see, the member 120 is a tension, and member 121 is compression. The value that we use here is by StatPro analysis. From the analysis, the maximum tension force is 27.67 kilonewton. The maximum compression force is 11.36 kilonewton. And then we calculate for the tension member that NED divided by NTRD must we compare not more than 1.0. From NED, we find the value of A, the value of A. So we use size here is 120 times 120 times 12.5 or square hollow section SSS. As you can see, this is a cross-section value that we are refer on the Eurocode. So the value on Eurocode is more bigger than the value that we calculate at A. So we use the value on the Eurocode, which is a 5,210 millimeter mm square. So for the NTRD, we put the value that we compare before it, which is 5.20 5210 times 275 times negative 3 divided 1. So we got the NTRD value is 1433 kilonewton. For NURD, this is the formula that we use as 0.9 NFY. So 0.9 A, the value that we use above is A, here is 520 times 410 times 10 negative 3 divided 1.25. So the value for NTRD is 1433 kilonewton. So after all that calculation, we need to verify that NED divided by NTRD which is NED, the value maximum tension force, divided by NTRD value. So we got value is 0.02, which is below than 1, so it's okay. For the compression member, NED here, we got it from the analysis, which is 11.36. So the size that we use, the size that we use is 120 times 120 times 12.5, same with tension. So the class of section in compression, this is the formula, and we got the value for the strain is 0.92. For the H, for this for this part, H divided by T, which is H is the size that we use is 120 divided by 12.5, so we got it value is 9.6. So H over T, which is here that we are calculate, uh is lower, about if we compare, and it is low than 15 strain, so we use this 15 times is 0.924, and we got the value is 13.86. So for the overall cross section classification, is class 3, and the resistance of class section NCRD, as you can see, is say we get it from the above calculation. It's same with the NTRD, which is NT for tension, NC for compressions, and it's same value 1433 kilonewton. And then we are designed for the buckling resistance of the compression member, NBRD, and we got the value is 1318.13 kilonewton. 0.92, we got it from here, which is the formula here is, which is started from here, AFY and CR square root, and then we got the value is 0.45. We got it for the value of the theta, I think 0.75. And then for the X calculation, the value at theta, we insert it into the calculation. So the value is 0.92, and then the 0.92 we bring the value into this NBRD, and we get the value is 1318.13 kilonewton. And then we compare the value. If the value is more than 1, so we use 1. If the value is lower than 1, so we use 0.92. So for NED divided by NBRD, so NED is 11.36 for the compressions, so we divided by 1318 for the value of NBRD, and the value that we got is 0.01, which is lower than 1. So for the NBRD is 13.18.13, is okay because it's larger than the value at the compression, so it's okay. So the use of 120 times 120 times 12.5 SSH in grade S275 still is acceptable.
Hello, my name is Kamaro Afif and my matrix number is CF190009. In this part, I'm going to explain a simple manner about the calculation of top chords and internal members and trusses. Based on the slide, the picture and equation marked in green represent the tension member, while the image and equation highlighted in red show the compression member and trusses. The main formula was provided in these two slides, with the design value of these two equations not exceeding 1. The second slide, which is this one, shows the buckling resistance of a compression member, which is NBRD. We can refer to the clause 6.3.2. Then we're going to move on to the next example calculation. Next, this is the example calculation at the left side, which is the internal member, at the right side, which is the top chord. So these are some of the data that were collected from the previous slide. So in order to find this, first we're going to find the tension member. We must satisfy, which is the value must not exceeding 1.0. So in this two equation calculation, which is okay. Next, we're going to find the compression member. Same with by using the previous slide, the main. So we're going to find the overall cross section between these two calculations is class 3. So we're going to find the resistance of class section and the design buckling resistance of a compression member in order to verify that our size is acceptable, which is for the internal member we're using 100 times 100 times 10 SHS in grade 275 still is acceptable. While for the top chord, which is use 50 times 5 UKA in a grade S275 still is acceptable too. That's all from me. Thank you.
Assalamualaikum and hi, my name is Muhammad Azizi Yusri bin Rusidi, and today I will explain about my part, which is design critical tension and compression truss member. From the step pro that we have been designed, our proposed design, we get the value for the tension, which is 50.66, while for the compression is 41.93. And then we move to the design part, which is maximum tension force and maximum compression force value we get from the step pro software. For the tension member, certify NED over NTRD must be less than 1.0. So from the NED value is 184 mm square, we decided to use a size of 100 times 100 times 10 of a square hollow section, which is a cross section 3490 mm square, is larger than 184. So we get the value for the NTRD, which is 960 kilonewton. For the value NURD, we get 1030 kilonewton. So NTRD is 960 kilonewton. So verify NED over NTRD equal to 50.66 over 960 equal 0.1, which is less than 1.0. That means the design is okay and acceptable. Next, we go to the compression member. We use same size as a tension, which is 100 times 100 times 10 with a NED 41.93 for the class of section in compression. The value of square root 235 over Fy is 0.924. And we check the overall cross-section classification is a class 3. And resistance of class section NCRD equal to 960 kilonewton. For the design buckling resistance of a compression member, NBRD equal to lambda AFY over gamma M1 equal to 739 kilonewton. And for the NCR, we get a value is 3199 kilonewton. And the value of LCR is 1730 for the alpha equal to 1.34. Lambda square root AFY over NCR equal to 0.55 for the angle of repose equal to 0.86. And value of lambda that have been calculated 1 over angle of repose plus a square root angle of repose square minus lambda equal to 0.77. And that's for the verifying. 0.77 is less than 1.0, which is okay. NED over NBRD equal to 41.93 over 739 kilonewton equal to 0.06, less than 1.0. NBRD equal to 739 kilonewton is larger than 41.93 kilonewton, which means that design is okay and acceptable. So we decided and we conclude we use 100 times 100 times 10 say hollow section in grade S275 still have been used for our design. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aiman Fifi bin Rosli. My matrix number CF1001C. Okay, I will explain about my part bottom chord, the calculation of tension member and compression member. Okay, before we go to the step of calculation, I will tell about the value that we get, value of tension and compression. Okay, the value of tension and compression we get from the data of analysis from step pro that we design. Okay, for the tension, we choose the member of 102. The value of maximum tension is 25.73. And then for the compression, the member from 85, the value is 21.43. Okay, now we go to the tension member calculation. First, we need to find the NED. Before we find the NED, we need to find the area of section, cross section. So the value is 94. So in this project, we propose to use the size of 50 times 50 times CL UKA of equal angle. So the cross section is 596 mm square. So bigger than 94. So it's okay. And then we use the we need to find the NTRD. So the value is NTRD is 156.48 kilonewton. And then we find the value of NURD. So the value of NURD is 65.21 kilonewton. So NTRD is 65.12 kilonewton. So we verify the NED divide by NTRD. So 25.73 divided by 65.12, so we get 0.4. So the value is lower than 1.0, so it's okay. Now we go to compression member. The value of compression member that we choose from the member 85 is 21.43 kilonewton. The size we use for this member also same like the tension. We use 50 times 50 times CL single angle. Class first we need to identify the class of section in compression. So we find the value of absolute. So the value of absolute is 0.92, and then we find the value of H divided by T, and then alpha. So we get the H divided by T is lower than 50 times absolute, and also the same B plus H is also lower than the value of 11.5 multiply absolute. So what we can say, the overall of cross-section classification in class 3. So we go to resistance of class section NCRD. The value is NCRD is 156 kilonewton. And then we go to checking the design buckling resistance of compression member. So we need to find the value of MBRD. Before to find this value, we need to find the value of S. So to find the value of X, we need to find the value of lambda and theta. For lambda is 1.17 and for theta is 2. So we can get the value of X is 0.27. So value of X 0.27 is lower than 1.0. So we use 0.27 and apply in this formula for MBRD. So we get MBRD is 42.25 kilonewton. And then from the value of NED and MBRD, we divide 21.43, we divide 42.25, so we get 0.51, so it's lower than 1. So we can say that MBRD 42.25 is bigger than NED 21.43, so it's okay to use. And then we can conclude that our proposed design for the member that we use size of 50 times 50 times CL UKA in grade S275 still is acceptable for our project, our design project. So that's all from me. Thank you.
Assalamualaikum. My name is Muhammad Afiq bin Syahrul Rizan, CF190142. Okay, so I will explain about the chapter 5. Chapter 5 is the design of connections. We have few connections, which is lap joints. The lap joint is the two plates in lap joints are simply lap over each other and bolt together. And then for the butt joints, Assalamualaikum. My name is Muhammad Afiq bin Syahrul Rizan, CF190142. I will explain about the chapter 5. Chapter 5 is the design of connection. We have a few joints, which is a lap joint. The lap joint is the two plates in the lap joints are simply lap over each other and bolted together. For the butt joints, a bolted butt joint is depicted, which is like this picture, this figure 5.1. The two plates being connected are aligned end to end in a butt joint, and cover plates are used to make the connections. Next, for the single shear and double shear, the shear strength of a connection is determined by the number of shear planes available. In our project, we propose we will calculate for the single shear plane and double shear plane. First, for the single shear plane, we use the M20 grade 4.8 and the bolts is 24 mm. First, we calculate the shear resistance. For the shear resistance per bolt, we use the formula of FVRD and the value is 68 kilonewton. Next, for the bearing capacity, we use the formula FBRD. For end bolts, the value is 0.694, and for inner bolt is 0.722. For the inner bolts, K1 is the smaller of, and the value is 2.5, same as for edge bolts. Next, to calculate the FBRD, we use this formula and we will get 182 kilonewton. Next, for the inner bolt, we use the formula also same FBRD, and the value is 189 kilonewton. So it states here clearly the resistance of the joint is controlled by the strength in shear. Therefore, the resistance of the tension splice as governed by the shear resistance of the bolt is 204 kilonewton. Next, for double shear plane, this one is the detailing, the drawing for the bolts. The shear resistant bolts are in double shear, and it's assumed that two shear planes pass through the threaded portion of the bolts. Shear resistance per bolt FBRD is 136 kilonewton. For the bearing resistance, FBED for end bolt is 0.694, for inner bolt is 0.722. Next, for the inner bolts, K1 is the smaller of, K1 equal to 2.5, and this one is 0.98. For end bolt, the value is 181 kilonewton, and for inner bolt is 189 kilonewton. It's clearly the resistance of the joints is controlled by the strength in shear. Therefore, the resistance of torsion splice governed by the shear resistance of the bolt is 408 kilonewton. Okay, that's all from me. Thank you.